Good. And testing. All right. We're good to go. So today we're going to finish up chapter 6. And then next week we'll have a review. And I believe then there's a break. Yeah. The week after next is spring break. So you get that whole week to study or panic or do what you do before test. And then we'll have the exam. Well, next week we'll have the lab, detecting signs of chemical change. And then we'll have an exam on the 27th of March. We don't have a lab today. I need a break too. Now, I do that. I put breaks in between labs in places where I think we might need some extra time to finish up this part. So we're not forced to rush through things.
Concerning this is chemical equations, I'm very happy about that, because I
Yeah.
imagine it's going to take me a minute.
It might take a little while for it to sink in.
Yeah, a little more than a minute.
Let's see. Pull out an extra. There we go. Okay. So now, retake control here. Chapter 6. So at this point, we're going to start getting into the mechanics of chemistry. And by that, I mean building the skill set so that we can actually do calculations to determine, all right, if we put these two things together in these amounts, how much do we get out on the other side? So these skills are aimed at that. First thing we need to do is develop a skill for calculating the formula mass for a compound. Right? Once you've learned how to write compounds, and we've gone through that before, type 1, type 2, type 3. Once you know how to write the compound, then it's important to know how much that compound weighs. And you can express it in one of two different ways. Let's see, I think I owe you something. Yep. That's great.
Thank you.
Oh, you're going to need one of these too. This is for today, and this is for next week's lab. So remember when we talked about atomic mass units? Those are ways to express how much an atom weighs. So when we're talking about atomic mass units, this is in terms of individual atoms. Right? So if you add up the mass of each individual atom in that formula, you get its formula mass. Right? So 10 would be 118.71, but you have 2 fluorines. So you have to have 2 times 19, and that gives you 156.71 atomic mass units for that molecule. Actually, it's a formula. Why do I say formula instead of a molecule? Because a metal and a non-metal don't make molecules, right? They make crystal lattices, positive ions, negative ions. This is the simplest whole number ratio of 10 to fluorine. You only get molecules when you've got a type 3 compound, where you combine non-metal with non-metal and they share electrons. When that happens, then you get a defined molecule that holds itself together in interactions with other molecules. But when you're talking about this one, 2 plus charge and a -1 charge, you have a crystal lattice. So that's why we use the term formula mass, because this is the formula for our ionic compound, the simplest whole number ratio. Okay. But occasionally I'll relapse, and I might say molecular formula or something like that. I'll try not to do that. Okay, so what's the formula mass of this compound, which is what? Assuming it's an aqueous solution. Right? So if this is an aqueous solution, this says it's an acid, preceded by hydrogens. Right? So we need to know what this is, which is sulfate. And then since it has oxygen in it, we don't say hydro, remember? So H become X, and we say sulfuric acid. Okay. But that's not the question. What's the formula mass for this one? So you need 2 hydrogens, right? And each one is that. Then you need a sulfur, and can I see that far? 3206. Thank you. 3206, and then 4 oxygens. Okay, just add them all together, and these are, at this point, we're saying atomic mass units. So just add those all together, and you get 98. Atomic mass units, when we're considering this formula in terms of 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. Okay, but that's not very convenient. When we start having to measure things, we don't have any balances that measure in atomic mass units. So the atomic mass unit concept is a starting point to get us to something that we can use. Remember, our standard for mass of individual atoms is carbon-12. That's defined as (12) atomic mass units. That particular isotope. Everything else is related to it. So we have this amount of atoms, and if we use this carbon-12 as our standard, then we say if we just change that to grams, then the number of atoms required to make that many grams is 1 mole. Right? So 1 mole of carbon-12 equals, that many grams. Right? So it's actually an experimental unit. If you gather exactly 12 grams of carbon-12 together, it will contain 1 mole of atoms, and then that mole is also equal to a number of atoms. Or 23 atoms. That's 1 mole. Now this one carries it out to several more decimal places, but if we stop at 3 decimal places, that's good enough for our work. And besides, over time, this number is refined with more accurate measurements. and it changes these digits out here, but it rarely ever touches those digits right there. So if we memorize this one, we're pretty good from now till the day you die. Okay, so a mole is that many objects. In fact, this defines the mole as that many atoms. But once we know how many objects is in a mole, how many objects are in a mole, then we can change this to suit us. It could be atoms, it could be formula units, like we were calculating earlier. Or, I don't know, if you want to be ridiculous, it could be that many chickens, is 1 mole of chickens. Okay, so anything can fit this. Once we've defined the number, then the mole could be anything. Formula units, actual molecules, okay, or it could be ions. Okay, so 1 mole is that many of whatever you want it to be. And that's useful because whenever we have this many equal to 1 mole, what do we have? We have a conversion factor. Anytime you have an equivalence, you can make a conversion factor out of it. So if you have so many moles in your hand, you can calculate how many atoms there are, or how many formula units, or whatever the case may be. Or you can go back the other direction. Okay. So anytime you have an equivalence, you automatically have a conversion factor. Okay, so how many eggs does 1 mole of egg contain? Just that number. Okay. Let's see, I forgot to identify this class. I better do that. And this is for exam 2. And this is chapter 6. There we go. Okay, so here's another concept. Once we've established what a mole is and how it's related to carbon-12 isotope, then in order to be of some use, those atomic mass units that are assigned to every element on the periodic table, and on this table, they're in the upper left-hand corner. Those decimal numbers that we have assumed are atomic mass units are also grams if you have 1 mole. So the average value, the weighted average for carbon, including all of its isotopes then, would be 12.01 grams per mole. Instead of atomic mass units, it's just grams. So that's nice, right? It can mean atomic mass units, it can mean grams. As long as you have 1 mole of them, it equals grams. We call that the molar mass. Right? So 1 mole of something weighs that much. In this case, nitrogen, 14.01 grams if you have a mole of those atoms. And you can do the same thing for compounds. Just add the carbon here together with 2 oxygens, and that compound, actually it's a molecule, weighs 44.01 grams per mole of them. So if you have 6.022 times 10 to the 23rd of these molecules, together they will weigh 44 grams. Okay? And there again, you've got a conversion factor. 1 mole of this equals that. Okay. So let's use what we've learned so far to calculate the mass of 2.5 moles of ethane. So we're given this compound, ethane, and we're also given 2.5 moles of it. And what we want is, how many grams does that represent? Okay. So we need a conversion factor that will cancel moles here and leave us with grams there. So there's our conversion factor. Whenever you see grams and moles as a quotient, think molar mass. So the molar mass of this compound is what? Well, let's see, we have 2 of those, right? And we have 6 of these. And so we just need a calculator. This is 2402 and 6.06. So I get 30.08. And that's grams per mole, molar mass of that compound. Now this is grams on top, moles on the bottom, so we can use it as it is, 30.08, like that. Then we just multiply that times 2.5, right? And I get 75.2 grams. If we're technically speaking, we should round that to 75 because they're only 2. And remember, all conversion factors are exact numbers. So they don't contribute, they don't limit your significant figures. Only this one does. So this should be 75, but it may not be on the slide. Oh, good. So we did take into account 2 significant figures here, 2 there. They rounded differently here. 3007, I get 3008. Okay. All right. Now, what if we have 50 grams of water? And we want to know how many moles that represents. Well, of course, you need your formula, right? You can't calculate molar mass unless you have a formula. You can't do it from the name. You have to make the name into a formula before you can calculate the molar mass. And water would be 2 times 1.01 for hydrogen, and then 1 times 16 for oxygen. So that's 18.02 grams per mole. Right? And we're starting off with 50 grams. Right? And we want to end up with so many moles. Okay? So for this one, grams is on the top, we need grams on the bottom and moles on the top. So remember, all conversion factors are equal to 1. You can flip that, doesn't matter, it's still 1. Right? So we can put 18.02 on the bottom if we want. And 18.02 divided into 50. I get 2.775. Moles. Those grams cancel. Now we can only keep 3, so it should be 2.78 moles. Okay. Now, why are we going to all this trouble? Because when we put together a chemical reaction in terms of a reaction equation, you've got to be able to convert back and forth between mass and moles in order to use that equation. And that's coming.
question.
Yes.
On the end of like these last few, they put the like, formula, everything like H2 at the end.
Uh-huh.
Will we have to do these on the test? And if so, do we need to put the formula at the end, or can we just put like 2.78 mole?
Most of them are going to be multiple choice anyway.
Oh, okay.
Yeah.
I was just curious if like putting the formula at the end is like part of the necessary like equation or not.
Yeah, I mean, if you're writing it in a lab notebook, something like you would need to identify it.
Okay.
Okay, aspirin has a molecular formula like this: C9H8O4. Let's see, that's actually, you want to know what the molecule looks like when you swallow it? It's a benzene ring, and then you have, let's see, that's 6, we need 3 more carbons. I think there's 1 there and 1 there. And then there's acetyl salicylic acid. Salicylic acid. Salicylic acid would be 1, 2, 3. 6 is 9. Okay, all the carbons are accounted for. Hydrogens. We've got 1, 2, 3, 4, 5. I need 3 more hydrogens. And I need 2 oxygens. Okay. So I think this one goes like 1, 5, 6, 7, 8 hydrogens. That's right. Oxygens. 1, 2, 3. I'm missing an oxygen. Okay, I painted myself into a corner. Never mind. I can't remember. Okay, so let's get back to the question. What's the mass of 1 mole of aspirin? So if we have 1 mole of this, all you need is the molar mass, right? Because that's grams per mole. So we need 9 times 12.01, and then 8 times the hydrogens, and then 4 times the oxygens. Okay, and that should give us the correct answer. Let's see. 364. I get 180.17. So it's probably C. It's the closest one. Okay. So what are we talking about when we write a chemical formula? There are 2 ways to look at it, actually. And we've mentioned them before. The chemical formula could be just that many atoms of each element stuck together. Okay, that's the microscopic view. So if we have N2O4, that one formula unit has 2 atoms of nitrogen and 4 atoms of oxygen. But if you look at it macroscopic view, something that we can actually measure, if you have 1 mole of this unit, then you actually have 2 moles of nitrogen and 4 moles of oxygen. So the ratios are always the same. If you have 1 molecule, then you have the ratio of 2 atoms to 4 atoms. If you have a whole mole of them, then you have 2 moles of nitrogen and 4 moles of oxygen in your possession. So if we have our ethane again, let's get kind of weak. Let me get a fresh one. There we go. So if you have 2.5 moles of this, the ratio is still the same. All right, 2.5. You have 2.5 total. Then for each carbon, you have 5 moles of carbon, and you have, let's see, what's 6 times 2.5? 15 moles of hydrogen. Okay. All right, there's our aspirin again. How many moles of carbon atoms, hydrogen atoms, and oxygen atoms are present? Well, if you have one formula unit, then you have 9 carbons, 8 hydrogens, and 4 oxygens. Okay. Moles of each one. So one formula unit represents 1 mole of the compound. So how many total atoms do you have in a mole of this compound? Well, you have 21, right? 6, 4, 12, yeah. 12, 9, 21 total atoms, moles of atoms. Now, this is the way the authors of the book think you should solve problems. And if you like that sort of thing, fine. I just put it up there to show you what they said. But I think it's easier to use the conversion factor approach. I think it's more flexible. This seems to be locked into talking about Avogadro's number. By the way, that is this right here. That's Avogadro's number. But the conversion factor approach is more flexible, I think. You say, what are you given? What do you need? And then your conversion factor is how you get there. You may need more than one conversion factor. You can chain them together. So let's see. I used to drive back to Atlanta more often than I do now because my family lives there. But both my parents have passed, and my sisters are both older than me. So I probably should get back more often. But if I were to go, I'd need to count the cost, as they say. How much is it going to take to get there? Double it so I can get back. And then maybe add a 10% buffer for driving around. I don't know, Atlanta, maybe 25%. So what do we need to know? Well, what are we given? Well, we're not actually given the values here, so you're going to have to look them up. What you're given is, how far is it? Right? It's about 385 miles from Beckley to Atlanta. Depends on which side of Atlanta you're headed for. If you're headed for the airport, it's on the south side, so you got to add another 30 miles probably. And then, where are you headed? What do you need? You need to know how much is it going to cost, right? So if we have this many miles to go, then we need to know some things to get where we're going. And it's probably, you don't have a conversion factor from miles to dollars. Right? You're going to have to use at least 2. So one of the conversion factors, in fact, if we work backwards, we need dollars on top here. So what do we need on the bottom? Well, when you're spending money, when you're traveling, it's usually for gas. So it'd be dollars per gallon. Right? And I think this problem at that time, it was like $2.80 or $2.85, something like that. I didn't spend that much yesterday. It was more like at Sam's, it was like $2.29, something like that. And then you need to know how to cancel your miles to give you the gallons, right? Because then you have to know miles per gallon. So that's particular for your car. Well, the way this problem was worked out was 385 miles and then 25 miles per gallon. You might get better if you have a 4-cylinder engine. You could get 30 or 35 on the road nowadays. But 25 would be pretty good for my van. And then how much does it cost per gallon? Right, so if we put $2.80, in fact, if you put $2.80 now, you've already built in a buffer. So we don't need to add any extra once we do the calculations. So this is in the numerator, denominator cancel. Numerator, denominator cancel. Leaves us with dollars. And now that we've done all, this is the thinking part. After that, it's just number crunching. So you got to be sure you put it in your calculator correctly. Right? And then ask yourself, is the answer reasonable? $43 to get there? Yeah, probably. 25 into 400 would be 8, and then 8 times 3 would be 24. That doesn't look right. 25 into 400. Oh, it's 16. Okay, so that doubles it. So you do sort of an estimate to see if the answer is reasonable. Okay? Which of the following is closest to the average mass of one atom of copper? Well, we could calculate it, or we could use some test-taking techniques and logic. How many atoms do you know that are going to weigh a gram each? None, right? So that's the only possibility right there. A very tiny, tiny, tiny weight would be characteristic of one atom of copper. But you can calculate it. Right? So how would we calculate one atom of copper? Okay, one atom of copper, that's where we're starting. Where we want to end up with, what does it weigh, right? So we don't know a relationship that goes from atoms to grams, but we do know one that goes from moles to grams. Okay, so 1 mole for copper is 6538, isn't it? No. 6355. 6355. Okay. And now we know a relationship between moles and atoms. Avogadro's number. Okay. Now we've got grams. And just do the calculation. Divide 63.55 by 6 times 10 to the 23rd, and you get this really, really small number. That's for each atom. Weighs that much. This is a trick question. Calculate the number of atoms in 63.55 grams of copper. If you recognize that as the molar mass of copper, then you know that represents 1 mole. And 1 mole is 6.022 times 10 to the 23rd atoms. Okay. How about this one? Which of the following 100-gram samples contains the greatest number of atoms? Okay. If you've got these samples of each magnesium, zinc, and silver, and they each weigh 100 grams, which one's going to have the most number of atoms? If they all weigh the same collectively, then which one's going to give you, which one's going to take the most number of atoms to give you 100 grams? the one that weighs the least. Right? Individually, each atom, the one that weighs the least, takes more atoms to make up 100 grams. Right? It's kind of inverse thinking. So the one that weighs the least is magnesium. That's the one that is going to have the greatest number of atoms in that sample. Okay, let's try this one. Say we have these samples, these individual samples of silver, zinc, and magnesium. I changed the order on us, didn't I? 107.9 grams of silver, 70 grams, see there's a zero in there, 70 grams of zinc, and 21 grams of magnesium. Now we want to put those in descending order of number of atoms. So we want the most number first, then the next, then the least number. So do we need to go to the trouble of converting these to number of moles or number of atoms? No. We can do it logically. 107 grams, 107.9 grams of silver is how many moles? It's exactly 1 mole, right? So that equals 1 mole. 70 grams of zinc is 65.39 grams of zinc is 1 mole. So 70 would be greater than a mole, right? 21 grams of magnesium. Magnesium is 24, right? So this is less than a mole. Now we put them in order, greatest to least. Greatest is more than a mole, right? So that's first. Exactly a mole, and less than a mole. So that's the order. Okay. Now, things get a little more complicated. If we have 100-gram samples of each one of these compounds, we want to rank them in descending order of number of oxygen atoms. When they say number of oxygen atoms, you don't necessarily have to calculate the numbers of atoms using Avogadro's number. If you calculate the number of moles, moles is a measure of numbers. So as long as you know the measure of that number, then you can put them in order. You don't have to waste time calculating actual numbers of oxygen atoms. Just moles of oxygen atoms will do. Okay? This is a case where I invoke Henry Ford. Set up an assembly line, because you're going to do the same calculation over and over and over and over again. So let's put them like this. Say water, and then dinitrogen monoxide, H6O2, that's probably propionic acid, and then carbon dioxide. Okay? We have 100-gram samples of each. So we're building our assembly line. We're starting from the same position, and we want to convert first to the number of moles of compound. Right? So we need a conversion factor for each one that's slightly different. Grams on the bottom. Why? Because here grams on the top, and leaves us with moles. Right? So we need a molar mass for each one. We did water earlier, 18.02. How about dinitrogen monoxide? Well, nitrogen is 1401, so that's 2002 plus 16, right? no, 2802. Nitrogen's 14.01. And then 16 for oxygen. So that's 4402. This conversion will tell us how many moles of the formula you have. All right. C3, okay. 3 carbons. 12.01. And then 6 hydrogens. And then 2 oxygens. I get 7409. And then carbon dioxide. So 1 carbon and 2 oxygens. 4401. Okay, so that's the number of moles of the compound. Okay, now we can take, because we cancel the grams, moles of compound. This is compound. Now we're going to convert that number of moles of compound to the number of moles of oxygen average. So this is going to be moles of compound, and this is the moles of oxygen, just like that. And the same all the way down. Okay, so what's the relationship? Well, for every mole of compound, how many moles of oxygen do you have? 1. For every mole of compound, you still only have 1 for this one. For every mole of compound, you have 2 oxygens. And for every mole of this compound, you have 2 oxygens. Okay, so that cancels the moles of compound and leaves us with moles of oxygen, and that's what we want. So at this point, now we've done all our thinking, we just do calculations. So 100 divided by 18.02 times 1 is 5.55. This is moles of oxygen in this column. Now we got 100 divided by 4402 times 1 is 2.227. And the next one, 100 divided by 7409 times 2 is 2.70. Rounded off. I could have kept a fourth one actually, because that has 4 significant figures. We're only going to put them in order, so it really doesn't matter. As long as they're not different at the 4th digit of the 3rd decimal place. Then the last one, 4401 and times 2 is 4.54. Okay, so if we put them in descending order from the greatest to the least, the greatest is which one? That one. So water's number 1. Second one, carbon dioxide. Third one, propionic acid. And last, there. Okay. So it's helpful to recognize the need for Henry Ford. Then if you set it up one way, you just do it the same way over and over again, just changing minor things that are characteristic and apply to that particular row. Okay, so they're the actual values. And then we can put them in order. Okay. Number of molecules in 0.325 gram tablet of aspirin. Does anybody take aspirin anymore? I mean, the full strength. I mean, lots of people take baby aspirin, like I do, for keep your platelets from sticking together. But people rarely take 325 milligrams of aspirin. It's pretty effective, you know, for headaches and fevers. But it could possibly have some side effects, particularly on young children. You don't want to give it to them. I don't even think they recommend baby aspirin for kids anymore. Use Tylenol most of the time. Okay, so if we take what we're given, 0.325 grams, and then we need the molar mass of aspirin, right? So that converts to moles, and then moles, we use this relationship of that many molecules, Avogadro, and gives us that many molecules. Okay? Okay, now for chemical reactions. Chemical reaction is sort of a symbolic statement of what's happening when two or more, actually one, when a chemical reaction occurs. We're describing it in terms of what are the reactants on the left-hand side. This is by convention. You always put the reactants on the left-hand side, and an arrow says these are the products. Okay? Sometimes you may see a double barbed arrow like this. That just means that the reaction can go forward and reverse. But at this point, we're just going to put a single arrow in there because we're more interested in the mechanics of writing the chemical equation first and balancing it. So what do we mean by balancing? When an equation is balanced, first of all, you have to write the compounds and the elements correctly. That's why we spent so much time early on writing compounds. If they're not written correctly, then your equation is doomed to failure. So you got to write the compounds correctly. Calcium is 2 plus, sulfur is 2 minus, that's good. Water is given. Calcium oxides, that's 2 plus, that's 2 minus. That's 1 plus, and this is 2 minus, so you need 2 of those. So those are written correctly. And the reactants are put in their proper place, products in their proper place. Now, how do we balance it? Well, as it turns out, this equation is already balanced. How do we know? Because the number of atoms, or moles for that matter, of a particular element the same on the reactant side and the product side. So you say 1 calcium, 1 calcium, 1 sulfur, 1 sulfur, 2 hydrogens, 2 hydrogens, 1 oxygen, 1 oxygen. It's balanced. Okay. Sometimes that happens when you write the compounds and it just automatically balances. But don't count on it. Okay. All right. So that's just what I said a second ago before I dropped my pointer. And a chemical equation can mean on the microscopic level or the macroscopic level, we could say 1 atom and 1 atom makes 1 molecule. Or we could say 1 mole of calcium and 1 mole of sulfur together make 1 mole of that molecule. And that's the more practical approach, the macroscopic. So what are coefficients? Coefficients are the numbers that you put in front of a compound. Once you write the compound, into your equation as a reactant or a product, from that point on, you can't touch it. That ratio of atoms in the compound is fixed. Leave them alone. The only way you can change the numbers is with coefficients. The number that precedes the compound. Okay? Now, if you're given a reaction which has, and the problem gives you masses of each of the reactants, say that they're going to be in a reaction, the coefficients do not change the mass. The coefficients only change the numbers of molecules, numbers of atoms. Mass is a different topic. Okay, so most chemistry books that I've ever seen give you an equation and they say one line, balanced by inspection. Have you seen that? Check out your book. That's probably what it says. Balanced by inspection. Or if they're slightly honest, they'll try to give you some helpful hints. But balanced by inspection, in my estimation, is a cop-out. You need some rules, a methodical approach to balancing equations, and that's what I'm going to give you. Okay, these are guidelines and helpful hints, but the helpful hints won't mean anything until we actually jump into an equation and balance it. So let's take this one. This one's already balanced. But let's take that one, unbalanced, and balance it, and we should come out with that answer. Okay, C6H12O6. You ever seen that before? That's glucose. So if we take C6H12O6, and when you're balancing, you don't necessarily need the states. You can put them in if you want. But you put your plus, and then you leave a gap here for coefficients. So we have oxygen. And remember, oxygen gas is diatomic. So if the problem says burn glucose in oxygen, you better write it O2. Right? What are the diatomics, just to refresh? Hydrogen, nitrogen, oxygen, fluorine, bromine, iodine. Those right there, plus hydrogen. Those are the diatomics. Okay, so now we're going to yield carbon dioxide. Right, so we leave a little space here. And water. Leave a little space there. Okay, let's see. Have we written everything correctly? That's the first test. All your compounds and elements are written correctly. Now we're going to set up a budget. What do you start with? Take each of the elements and write them down the left-hand side. Hydrogen, oxygen. That's everybody. Believe it or not, in all that mess, there's only carbon, hydrogen, and oxygen. So then, on this side, you tally how many of each one there are. So let's see, 6 carbons, that's it. Hydrogens, 12. Oxygens, you have 6 plus 2 is 8. That's where you're starting from, reactant side. Product side, 1 carbon, 2 hydrogens, and 3 oxygens. Okay? So you can tell at a glance that we're not balanced. Right? You got difference here, difference here, difference here. So the next helpful hint is to check out your equation and look for single elements. Hold those to last. Right? Don't put any coefficients in front of them unless you have to until the very end. Why? Because when you put a coefficient in front of an element, you're only changing that one. If you put it in front of something like this, you're changing carbon and oxygen, And that might mess up your balance that you previously acquired. So save the elements to last. Okay, now, where do you start? Well, it's not always easy to determine where to start. So if you can't figure, if you don't have experience on where to start, then just start at the top. Eventually you'll get there. It might take you more steps to do it that way than if you have some intuition about where starting would be better. But if we start at the top, we have 6 carbons on this side, we need 6 carbons on that side, right? You do it with coefficients. So that changes the carbons to 6. It also changes the oxygens to 12 plus 1 is 13. Okay. So if we look at hydrogens next, right? Because you've got a prime number here and an even number there, you probably don't want to tackle that right away. Maybe it'll work itself out, which often happens. So let's look at hydrogens. We got 12 hydrogens here. It only occurs in one place here. So if we say 6 times that, that gives us 12 hydrogens, doesn't it? It also gives us 6 oxygens plus 12 oxygens is 18 oxygens. 6, 12, yeah, that's right. Okay, now oxygens left over. And all we need is a coefficient in front of that one. But we have 18 required. We've already got 6 here. So how many does that mean? We need 12 more, don't we? So if we put a 6 here, that's 12 plus 6 is 18. And you're balanced. And using this budget system, you can tell in an instant that you're balanced. You don't have to go back in and count things. It tells you right there. Okay? So that's your introduction to my budgeting system. Now we're going to go next step. That was a fairly simple equation. Okay. So the goal is to have whole number coefficients only, right? But sometimes it's useful to reach a balance with a fraction, like this. It's an intermediate step. If you find yourself with a fraction in front of one of them, then all you have to do is multiply through by the denominator of that fraction, and you get rid of the fraction, plus you change all the others. Like we multiply through by 2, then we have 2 here, 25 here, because the fraction's gone now. 2 times that is 16, and 2 times that is 18. That's okay. And very often, it's the quicker way to get where you're going, to use a fraction. That's one of my helpful hints. Now, why does that work? Because you've already established the ratio of 1 to 25.5 to 8 to 9. That ratio in a balanced equation is fixed. It never changes from that point on. So if you multiply through by some other factor, you still have the same ratio, right? So the ratio of this to this to this to this is the same as that to that to that to that. Okay, so let's take this example. This is a little more complicated. What is this? Ammonium phosphate. Calcium chloride. Calcium phosphate. Ammonium chloride. Right, so if we react those things together, you need another trick to help simplify things. Notice you've got all these polyatomic ions, right? Look to see if the polyatomic ion remains intact from reactants to products. Ammonium only occurs here, and it only occurs there. Phosphate occurs here, and it only occurs here. So, for budgeting purposes, you can write down the left-hand side. Let's see, maybe I'll do it in the slide. Here we go. You can keep your polyatomic groups together for balancing. Okay, it saves a lot of effort rather than busting them apart to tally nitrogens and hydrogens and phosphorus and oxygen and calcium and chlorine. It'll work that way. It just takes a whole lot longer and a lot more effort. So here we go. Initial for the reactants, right? We got 3 ammonias, right? See that subscript? We got 3 of these groups. What's next? Phosphate. We only got 1 phosphate. We got 1 calcium and 2 chlorine. That's our initial tally for reactants. So on the other side, we have 1 ammonia right here. We have 2 phosphates right here. See that, 2. We have 3 calciums and 1 chlorine. Okay. So you can tell at a glance that we're not balanced. So where do we start first? Well, there's a toss-up. Let me see where I started for this animation. Okay, these little red things, they mean order of operation. So the first thing I do is put a 3 in front of this one. That's just so when we get them all out here, if you go back and look at them, you can say, which one came first? This one came first. So with this 3 in front of here, that changes our calciums to 3. And I skipped one. Let's go back. There we go. That gives us 3 calciums and 6 chlorines on this side. Right. Then for the second one, I'm going to put a 6 in front of this, so that I can have 6 chlorines because I got 6 of them down here. So if I do that, that gives me 6 chlorines and 6 ammonias. Okay, move back up. Why is it skipping so far? Okay, so now we have, wait a minute, I went too far. There. Okay, so at this point, we've got 6 in front of here. We did this one first, changed our tally, and then we did this one with a 6 in front. So that changed the number of ammonias. So now the ammonias are out of balance again. And 6 chlorines. Chlorines are good. That's what we were aiming for with this 6, give us the rough number of chlorines. But we changed the ammonia. So now we need to go change the ammonias as our third step. So we need 6 ammonias. That means 2 times this 3. Right, so that gives us 6 ammonias, and the ammonias are balanced. So now we want to balance the phosphates. So we need a 2. Right, well, actually we already got a 2 there. So we just did the ammonias first, now we're doing the phosphates. So we got 2 phosphates. And the calciums also. So that's 6236, 6236, and we're balanced. Okay, so which one of these is correct for a balanced equation? That's the ideal because it's the simplest whole number ratio. Notice that the ratio 2521 and 41022 is, well, no, that's not right. No, that was not right. Let's see, 2, 1, 2.5, 1.5. So this is technically the same ratio of reactants and products, but they're fractions, and we want whole numbers. Okay, which of the following is true concerning balanced chemical equations? There may be more than one. The number of molecules is conserved. Is that true? No. Number of molecules might be different on one side than the other. Coefficients tell you how much of each substance you have. That's kind of a tricky play on words. How much means what's the mass? So the coefficients tell you not how much you have, but how many you have. Atoms are neither created nor destroyed. That holds true for a balanced equation. Coefficients indicate the mass ratios? No. Mole ratios. Sum of the coefficients on the reactant side equals the sum on the product side? No. Only the number of atoms conserved. That's the only thing that's true of all those statements. So here's one where we say, what's the balanced equation for heating sodium bicarbonate to produce sodium carbonate, carbon dioxide, and water? And my general chemistry students do that in the lab and do the calculations. So in order to heat this to produce these things, this is the reactant, these are the products, right? So we need to write sodium bicarbonate. Okay, bicarbonate is an archaic version. Bi means hydrogen. So sodium bicarbonate. Hydrogen carbonate is the polyatomic ion. If you look it up in that list I gave you, you'll find that HCO3 is -1 charge. +1 charge, that one's balanced. Now it produces what? Sodium carbonate. That's a 2- charge. This is a 1+ charge, so we need 2 of them. What else do we have? Carbon dioxide and water. Okay, so now we have our compounds written correctly. I just need to give myself some room for coefficients. There we go. Now we do our tally. So here's sodium. Notice that the bicarbonate does not remain intact. So we have to write it. Actually, we could take the carbonate out, or we could just bust everything apart. Why don't we do that? Just see how difficult it is. Hydrogen, carbon, oxygen. So we have 1 sodium here, 1 hydrogen, 1 carbon, 3 oxygens. We have 2 sodiums here, hydrogens, 2 hydrogens, okay, 2 carbons, and oxygens, 3, 4, 5, 6. Okay, so where do we start? We'll start at the top. So we have 1 sodium over here and 2 over here. This coefficient will give us 2 sodiums, and it'll give us 2 hydrogens, and it'll give us 2 carbons, and it'll give us 6 oxygens. We're balanced. 1 step. Okay?
That was easy.
Sometimes it happens.
So the answer is C, I guess. So I see 2. Yeah.
Yep.
I like that one. Can the whole test just be those?
If the world were that simple.
That would be easy.
Okay. So let's see. 4 molecules of iron react with 3 molecules. Coefficients in a balance. I thought that horse was dead. To produce 2 molecules. Oh, I see what we're getting at. We're using that to generate conversion factors. So once you've got a balanced equation, you have the potential for a whole host of conversion factors. because 4 of these ratio to 3 of those. 4 of these ratio to 2 of those. 3 of these ratio to 2 of those. Okay, so that's 1, 2, 3, and then you can flip them. So you actually have 6 conversion factors total. It just depends on which ones you need. So in this case, if we have 4 moles of iron, 4 moles of iron produces 2 moles of iron oxide, iron 3 oxide. And the ratio is equal to 1. 4 to 2 is the same as 2 to 4. Right? We just put this one up here and this one down here. Is equal to 1. We have a conversion factor. Okay. Okay, so they want us to balance that equation. That's okay. We can do that. We're masters by now, aren't we? C, oops, that's not a C. C2H6. We're going to burn it and make carbon dioxide and water. Right, so we have carbon, hydrogen, oxygen. 2 carbons, 6 oxygen, 6 hydrogens, excuse me, 2 oxygen. And on this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay, so we'll just start at the top. 2 carbons we need over here. That's 2 there. But that gives us 5 oxygens, right? Is that true? Yeah, that's true. How about hydrogens? We got 6 here, and we need 6 here. So what if we say 3 gives us 6 hydrogens there? That gives us 3 plus 4 is 7. Now, we saved oxygen till last, right? So, how do you get 7 oxygens out of that one? There's no number. Multiply it by 2, a whole number multiplied by 2 could give you 7. So we're going to use a fraction as an intermediate step. So 7 halves of that oxygen gives you 7 oxygens, right? Because oxygen is like this. And if you have a half of that, then you got this much times 7 equals 7 oxygens, okay? Now that's our intermediate step. We want whole numbers. So now that we've got 7 oxygens on this side, we multiply the whole thing through by 2 because the ratio is established now. We're balanced, but we want to get rid of a fraction. And the ratio will not change as long as you multiply the entire thing through by the denominator. So that gives us 2 here, 2 there. That gives us 7 there, 4 here, and 6 there. So the coefficients are 2, 7, 4, and 6. Okay? I think I've shown you all my tricks, helpful hints at this point. They're on individual slides in there, but I figured it would make more sense if we actually just used them. Now, what do we mean by stoichiometry? Stoichiometry is the study of chemical reactions in terms of input and output. So if you have so many grams of this reactant and that reactant together, how many grams of product are you going to get? Right? So we're going to use what we've learned so far to relate the masses of the reacting chemicals. Now, it's a simplified version. It's not always masses, but for our purposes, that's where we're starting. Yeah, and that's the author's idea of simple. So if methane reacts with oxygen and air to produce carbon dioxide and water, and ammonia reacts in oxygen and air to produce nitrogen monoxide and water, write the balanced equation for each one. Right? So this is just part one of the exercise. So let's do methane first. Sometimes after you've done these so many times, you don't even need to set up about the budget. But it's always a good fallback position. Methane plus oxygen yields carbon dioxide and water, I think. Yeah. Okay. So we have carbon, hydrogen, oxygen. 1 carbon, 4 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. Okay, we got 1 carbon on either side. Hydrogens, we need 4 on this side, but that gives 2 plus 2 is 4 here. Now 2 times this gives you 4 here, and we're balanced. Okay, that go too fast? Okay. Now if that one's balanced, let's balance the second one. Ammonia plus what? Oxygen in the air, okay, yields what? Nitrogen monoxide and water. Okay, so we have nitrogen, hydrogen, oxygen, nitrogen, hydrogen, oxygen. We have 1 on this side, 3 hydrogens, 2 oxygens, 1 nitrogen, 2 hydrogens, and 2 oxygens. Okay, so let's see. Where do we start? Well, the only one that's out of balance is hydrogens. How do we get 3 hydrogens over here? We could use a fraction. Well, there's another trick. It's called cross multiply. If we say 2 times this one and 3 times this one, because that's where our hydrogens are, then that gives us 6 hydrogens here and 6 hydrogens here. Then we change this one to 2 for a nitrogen, and this one has affected oxygens, which are 3, 4 oxygens. Okay. But we need 2 nitrogens. So that's 2 here. Now we're 2 plus 3 is 5. So now we can use our fraction. 5 halves gives us 5 here. Now we're going to apply the whole thing through by 2. That gives us 6, 4, 5, and 4. Okay. All right. So now, let's see. Let me change this to 6. Change this one to 4. Change this one to 5. And this one to 4. There. Now we've got our balanced equations as instructed. All right. That's part 1. Let's see. What do they want for part 2? What mass of ammonia will produce the same amount of water as 1 gram of methane reacting with excess oxygen? Okay, this is a little complicated for our first dance with stoichiometry. So let's break it down into 2 problems, right? So what mass of ammonia would produce the same amount of water as 1 gram of methane? So 1 gram of methane is actually the starting point. And this is excess. Right? So we got plenty of oxygen. And that makes sense. If you burn methane in the air, there's no limit to the amount of oxygen. But we are limited by 1 gram of methane. So the same amount of water. So this is where we're headed. We want to know how much water is produced. Right? When you have a balanced equation, you've written all your compounds and elements, you balance the equation, you're given a mass, you can't go anywhere in that equation until you got moles. Right? There's a great wall separating all of the reactants and products. You can't get over that wall unless you're moles. Right? Grams are too heavy. Can't climb the wall. So we convert to moles. Once you've got moles, then you can move anywhere you want to. So how many moles of methane do we have? Well, you need to convert. Right? Grams to moles. Notice we got a quotient here. That's molar mass. Molar mass of methane is what? 12.01 plus 4.04. Right? 4 hydrogen. So that's 16.05. See how we're doing on time. Anybody getting sleepy, need a break? Okay. So we're going to find out how many moles that represents. We just need 1 divided by 16.05. 5 is 6.23 times 10 to the minus 2. 6.23 times 10 to the minus 2 moles of methane. Okay, now that we got moles, we can go anywhere because the ratio, a conversion factor that we need, can be implied from each of the coefficients. We want to get over here. So if we have this many moles of methane, the conversion from methane to water is just the coefficients, right? So we've got 1 methane and 2 waters. So the conversion now is just 2 times that. 1.25 times 10 to the minus 1. And that's moles of water. Okay?
So for 1 gram of ammonia, you get
No, 1 gram of methane.
methane. Okay, I was looking at the wrong one.
Yeah. See, we
You
have
get 1.25.
right the same amount of water. Right? Same amount of water. Now we know how much water is produced from this reaction. It's the same amount here as here. That's what it says. Same amount of water here and here. So now we know that the number of moles here is 1.25 times 10 to the minus 1. And the second question then is, what mass of ammonia would be required to produce that much water? So now we can move backwards to ammonia. We just take this and use a conversion factor for the second equation, right? So we're going to get rid of water and leave us with ammonia, which is 4, right? 4 and 6. Right? So 2/3 of that value is 8.31 times 10 to the minus 2. Moles of ammonia, right? Because that one canceled that one, leaves us with moles of ammonia. We're almost there. Mass of ammonia. How do we get mass of ammonia out of a moles? Molar mass. Right? Now you need a conversion that will take you from moles to grams of ammonia. So we need the molar mass of ammonia, which is 14.01 plus 3 times 101, 3.03, 1704 leave us with grams. See if I still got it in my calculator. Yep. It's multiplied. So I get 1.42. 0.42 grams of ammonia. So that says that if we start off with this many grams of ammonia and this many grams of methane, they each, in their separate reactions, produce the exact same amount of water. Okay, so there's all the calculations. Let's see, there we go. That's how much water. We'll take that much water and convert it back to ammonia. And Bob, your uncle. Okay, any questions? All right. Okay. Percent yield. Every chemical engineer understands the concept of percent yield. Why? Because chemical engineers are in the business of making money for their employers. That's why they get paid so much. If you want a bachelor's degree that pays lots of money, be a chemical engineer. Anyway, the yield is an expression of the ratio of how much you actually get out of a reaction versus the theoretical amount, otherwise known as the stoichiometric amount. So with that 1 gram of methane, we get so many moles of water, and we could convert that to grams, right? Just use 18.02 grams per mole. That's what we would expect to get from that reaction. All of that methane converted to completely into products would give us that much water.
So it's pretty much the percent error. Like what we
It
looks
it's
similar
that concept. Yeah.
Yeah. What you expect to get out of your gun,
Right. And
then what you're actually getting.
Right.
And then that,
Except,
whatever it is the room for error, sort of.
right. Percent of error in this case, the actual yield would be theoretical yield minus your loss.
Yeah.
Yeah. That would be your actual yield. So the theoretical yield you determine, and this is in mass. Right? So the theoretical yield is the mass of product of interest, and then what you actually get from the reaction for that product in mass. And it's just that ratio times 100. So why is that important? Well, reactions rarely ever give you, in fact, I can't think of a single one that gives you 100% yield every time. The best you can do is get up into the 90s if you're lucky. So what do you need to know that for? Because if you expect to get a certain amount from the reaction, the actual yield, then you've got to back calculate through the theoretical yield to find out how much do I need to start with to actually give me that amount that I want. So that's the chemical engineer's responsibility to do that. And when your yields get really low, then you know that your reactors need maintenance. Okay, and then what you do is hire some poor college student on the LSU campus to climb into your reactor and clean it for you, because they're expendable. And they make some extra bucks that way. Let's see, where am I? I went too far. Here we go. Okay, so what would be the percent yield of a product if the theoretical yield and the actual yield are this? That's the theoretical, and this is the actual. You just take 4.5 divided by 5.6 times 100, and it's about 80%, which is not bad. I mean, when you consider Fritz Haber, when he was reacting nitrogen and hydrogen to produce ammonia for the weapons industry in Germany, leading up to World War I. He figured out how to increase his efficiency. Right? That's not balanced either. Let's see, two here. Yeah. What he discovered was that in order to make the reaction go, he would have to heat it up. Problem is that this is an exothermic reaction, and hopefully we'll get to that in the future, which means it produced heat out here. If you increase the temperature, that's like adding heat to this side, and it drives the reaction the wrong direction. So he added a catalyst, just finely divided iron, and that made the reaction go faster. So he produced a certain small percent, like maybe 15% or less of product, and nitrogen gas, hydrogen gas, ammonia gas have different boiling points. Right? So you can cool the whole mixture down. You can just draw it off, draw part of it off, cool it down. This one comes out first. It has a higher boiling point, so it will condense first. These guys will stay gases. So you extract that out, take these, send them back through the reactor. You do that 4 or 5 times, and you got your efficiency up over 80%. Okay. Let's see. Pennies produced prior to 1982 were composed of 95% copper. That's true. I think the other element in the alloy was zinc. Copper and zinc, 95% copper prior to 1992. These pennies weighed 3.11 grams. How many atoms of copper were present in this pre-1982 penny? Right. So if the penny weighs 3.11 grams, right, how much copper does it have? 0.95. Right. Remember, percent is a dimensionless number. So in fractional terms, this is how much copper you have, 0.95 times that. So that would be what? Did you get 2.95? 2.95 grams of actual copper. And then convert that to atoms. We need to do molar mass. Let's see. Get close enough to see it. 6355. There we go. And then we want to convert moles to numbers of atoms, right? Because that's our choices. 6.022 times 10 to the 23rd atoms per mole. So you just take this, divide by that, times that, and you got your answer. 2.8 times 10 to the 22nd atoms of copper. Okay. Now, while I'm thinking of it, if you have a reaction that's not in terms of mass, you got the balanced equation and you're given something else besides mass, all you have to do is figure out how to convert it into moles before you can go to any other place. So mass is simple. We've done that one. If you have solutions, we haven't talked about solutions yet, have we? Okay. Then you just need concentration and how much of it, you can determine moles of that. So there are various ways to determine the number of moles to get from one place to the other. So that's where we're headed. So this, let's see, 2-liter bottle of carbonated soda on average of 0.2 grams of glucose per 100 mils. We metabolize it in the body by this same reaction. This is the overall reaction of metabolizing glucose in your body. It doesn't happen in one step. It happens in many steps. And there's good reason for that. This is an exothermic reaction. If you conducted that reaction in your cell, it would incinerate the cell, right? So we do it in steps. So we can extract the energy little by little by little. And these molecules have lots of energy stored in them. So that's why we breathe in oxygen and exhale carbon dioxide. Okay? And the water that's produced here just becomes part of the cell matrix. Right? And if you get too much of it, of course, your kidneys flush out what you don't need, along with waste products. To determine the number of grams of carbon dioxide produced after you consume 10 2-liter bottles of carbonated soda, my goodness, hope that's not all at once. Then you balance your equation here, right? And we found that was 6 here, 6 here, and 6 here. Right? Then you say, what are you given? Right? So you're given 0.2 grams of glucose per every 100 mils. Well, how much total glucose is that? Right? So you need 1,000 mils per liter, and you actually have 20 liters because you got 10 2-liter bottles. Right? So that gives you the number of milliliters of soda, and that cancels here and gives you the number of grams of glucose. Then we can convert glucose to moles of glucose and convert moles of glucose to moles of CO2. Then we convert it back to grams and find out if you consume 10 bottles of 2-liter soda, you're going to exhale 59 grams of carbon dioxide, which is a lot. But that's only from the glucose. What else does soda have in it? Why does it pop? It pops because it has carbon dioxide dissolved in it. Right? So this is the minimum. And then whenever you burp, you're burping up that carbon dioxide that came out of solution when you drank it. So you're actually getting rid of more carbon dioxide than that.
And there was your yield.
Yep. Okay, so that's it for today, and we'll pick up with a review next Friday, however long that takes, and we'll go in the lab and do the what's it? Detecting chemical change. It should be a fun lab. You have several different things that you do. Observe color changes and production of gas, maybe a precipitate forms. This is more of an observational lab than a quantitative lab.
I feel like I'm missing something, and I'm going to feel like an idiot when I actually ask this question.
Okay.
Okay, on like that slide right before the last one, right when we were doing the, right here.
Yeah. Was it missing?
Where did the 6.02 go? Or where's it from? Is that the 6.022, the one thing? You had the slide, I just I'm going back to it. So I'm confused where we got the 6.02 at.
Oh, that's Avogadro's number.
That's that one, okay.
Yeah.
I knew I feel like an idiot.
It just-
I wanted to clarify.
It just left out.
Yeah, I was like, where's that?
It left out the third decimal, didn't it?
Yeah, I was looking at it and I was like, I feel like I know what it is, but it's better to double check sometimes. You know, it's better to feel like an idiot now than on test day.
Oh, yeah. Good point.
Yeah, that's how I like to look at it.
Let's see, is everybody sign in? 3636? Yep, everybody's that's here is counted for. And those who are not here are not accounted for. Who knows where they are? Let me slide this in its proper place. 36 right here. Oh, guess what next Friday is? If this is the 6th, next Friday is the 13th.
Ooh.
It's a good thing we're not having an exam on that day, right?
Yeah,
We're just doing a review.
that would just be cruel of you to schedule a test on that.
Mhm.
Good luck to all of you.
And watch out for the hexes.
Yeah, right.
Yeah, unless you have them now. If you've got it done, I'll take it. I got one already.
Yeah, I turned mine in because I was like, if I hold on to it another week, it's just gonna be gone. I'll be like, oh yeah, that thing. Oopsies. Watch next week. I'll show up and you'll ask for them, and I'll be like, did I turn mine in? Where's my paper?
Yeah, you need to tie a string on your finger or something.
I have so many alarms and notifications and like emails I send to myself just as reminders that ain't even funny. I guess where I'm just so focused on the schoolwork, I kind of forget like the physical world for a bit.
Yeah.
Have a good day.
You too. All right, stop the recording.